Alright guys, so in this set of notes we're going to talk about derivative concepts and applications. So we're just going to go through a few different topics. We want to go through it kind of quick, don't want these notes to take too long. I really just want it to be mainly a reference for you to use. So first of all, let's talk about the limit definition of a derivative. There are two different ways to find the derivative of a function using a limit definition. One way is with the standard form. It's where you have some function f of x, and what you're going to do is you're going to plug into it x plus delta x, or it's just easier a lot of times to put h instead of delta x, minus f of x over, I believe it would just be h at that point. And you just find the limit of this as h approaches 0. Okay, that's the standard form. And in case you guys forgot, what we're looking at here basically is the slope formula for a secant line, or the average rate of change. But as you let h approach 0, it goes from being a secant line to a tangent line, and it therefore becomes the derivative. Okay, so that's the standard form of the limit definition of a derivative. Now there's the alternative form as well. The alternative form looks like this. You have your function minus another value plugged in somewhere over x minus c. And still, that's just still the difference quotient, or the slope formula for a secant line. But if you take the limit of that as the x value approaches c, that also will just tell you the derivative. But here's the difference. This formula tells you the derivative at a specific point, c, whatever the number is that you're plugging in. So that's the limit definition of a derivative. There are two of them. You'll see how those types of questions will be asked when you go through the worksheets later on today. Let's move on to our next slide here. The definition of differentiability. What does that mean? A function is differentiable at x equals c if the derivative exists at c. Now there's a couple of criteria that have to be met. So the criteria for differentiability include the following things. First of all, the function needs to be continuous. That means there should be no holes or gaps or jumps. That should mean that the functions should exist at c. In other words, no holes should be allowed, or vertical asymptotes. Also, the limit needs to exist at that point. That means no jumps are allowed. You can't have a function going here and then all of a sudden jumping up here, because the limit from the left and right are different, which means the limit doesn't exist. Also, whatever that value is for the limit, and whatever that value of the function is, they need to be the same. Okay, so those are the three criteria that need to be satisfied in order for a function to be continuous, and all three of those criteria have to be in place in order for a function to be differentiable. But more is required for a function to be differentiable than just to be continuous. It also has to have the same derivative from the left and from the right. So the limit, I don't want to put that there yet. The limit of the derivative of the function as x approaches c from the right needs to equal the limit as x approaches c from the left of the same derivative. And what this is basically saying is that the slope from the right needs to be the same as the slope from the left at that specific point. So here's an example of what's not okay. No cusps are allowed. Okay? Now when they ask for explanations on these, you can't say no cusps, okay? You have to say this. That's how they want you to write it. But like for instance, I'll show you a cusp. A cusp would be something like this. Okay, as you guys can see, the slope on the left side is negative and the slope on the right side is positive, and there's a sudden sharp turn there. They're not equaling each other at that point. So the slope from the left has to equal the slope from the right. And then finally, you can't have any, well, let's just say f prime has to exist, which is kind of obvious from the definition up here. Now, what that really means is no vertical tangent lines. Okay, so if you have a function that looks like this, for instance, well, like maybe like right about here, it looks like we might have a vertical tangent line, and that's not allowed. So a vertical tangent line means you have an undefined slope, and since the derivative is a slope, if you have a vertical tangent line, that means the slope doesn't exist, which means the derivative doesn't exist, which means your function is not differentiable. So really we have three criteria that we need to make sure are in place for a function to be differentiable. It needs to be continuous, the slope from the left and the right have to be the same, and the function must exist. Okay, so that's the stuff that's required for differentiability. Let's go ahead and move on here. Solving related rates. I'm just going to leave this here and let you guys make sure you have it as a reference, because we're going to do some related rate problems on the practice sheet, and these steps will come in handy, but they're not really useful unless we're actually doing a problem. So for now, I'll just leave it at that. Let's go ahead and talk about position, velocity, and acceleration real quick. All right, so let's assume for a second that S represents the position of a function at time t. The average velocity would be, don't like how thick that got, okay. The average velocity can be found by doing your regular old slope formula. Plugging in b and a and then dividing by b minus a, okay? The instantaneous velocity is found by doing the derivative. Average acceleration is where you plug 2 points into your derivative and find the average rate of change of your derivative instead of the original function. Okay? Instantaneous acceleration would be the second derivative. Okay? And speed is the absolute value of velocity. So if your velocity, for instance, is s prime of c, you would take the absolute value of that. All right? Now, let's interpret position and velocity a little bit here. On this chart down here, position and velocity can be positive or negative, and they also can be on vertical or horizontal axes. So let's start off with position. With position, if it's positive and on a vertical axis, that means that the location is above 0. If it's on a horizontal axis, it's to the right of 0. It's just telling you where the object is located. If your position is negative, then on a vertical axis, that would mean that you're below 0. Or on a horizontal axis, that would mean that you are to the left of 0. Now, when velocity is positive or negative, it means something slightly different. On a vertical axis, that means you're moving up if the velocity is positive. But if you're on a horizontal axis, a positive velocity means you're moving to the right. So notice the difference between position and velocity here. They both have to do with up and right, but the difference is position just tells you where the object's located, whereas velocity tells you what direction it's moving. Okay, and so when velocity is negative, if you're on a vertical axis, that means you're moving down. And if you're on a horizontal axis, that means you're moving right. Now, a lot of times, the questions that you guys will be asked is whether or not a particle or something is speeding up or slowing down. And that depends on two things. An object can be determined to be speeding up or slowing down by looking at velocity and acceleration. Anytime velocity and acceleration have the same sign value, they are speeding up. So in these two cases here, we're speeding up because in the top left quadrant, we have a positive acceleration and a positive velocity. In the bottom right quadrant, they're both negative. So in both of those cases, we're speeding up. But anytime acceleration and velocity are opposite signs, they're slowing down. So in these two spots, we would say it's slowing down. All right, so that is position, velocity, acceleration facts that you're going to want to keep in mind. Now, you're going to see some questions about comparing f prime, and f double prime. So, what can we conclude about the function f if its derivative is positive? Well, if f prime is positive, that means that f is increasing. Likewise, if f prime is negative, that means that f is decreasing. So in other words, when the function f is moving in an upward direction, that would mean that its slope is positive. And when f is moving in a downward direction, that would mean that its slope is negative. Now, what happens when the derivative is negative or undefined? Well, it's a critical value for sure. But it could be, so I'll put and or, it could be a relative min or a relative max. Okay, and the way that you could tell is, does f prime go from negative to positive? If f prime is going from negative to positive, that would make a relative minimum. If f prime goes from positive to negative, it's the opposite. So if f prime is going from a positive slope to a negative slope, or if f is going from a positive slope to a negative slope, in other words, f prime is going from positive to negative, that would mean that f has a relative max. So that is what we can conclude about f based on the sign values of f prime. Now let's go ahead and move on to the next part here. What can we conclude about f if its second derivative is positive? If its second derivative is positive, that means that f is concave up. And if its second derivative is negative, that means that f is concave down. And what can we conclude if f double prime is 0 or undefined? Well, if f double prime changes signs also, so it can't just be 0 or undefined, it has to change signs. And it doesn't matter if it's from positive to negative or negative to positive. But if it's 0 or undefined and it changes signs in either direction, then we have a point of inflection there. Okay, so there's another little fact for you. All right, let's move on down to the last chart that we have here. Notice the chart looks the same as this one, but the question is different. What can we conclude about f prime? Not f, but what can we conclude about f prime if f double prime is positive? Well, I got news for you guys. If I'm asking what can I conclude about f prime based on f double prime being positive or negative or 0, that's really the same thing as this chart up here. Going from f to f prime is pretty much the same thing as going from f prime to f double prime, because f prime is the derivative of f, just like f double prime is the derivative of f prime. So I'm going to have all the same answers here. It's just that instead of writing the letter F here, I'm going to put F prime. So what can we conclude about F prime if F double prime is positive? Well, that would mean that F prime is increasing. And what can we conclude about F prime if F double prime is negative? Well, that would mean that F double prime is decreasing. And what can we conclude about F prime when F double prime is 0 or undefined? Well, that means that we have a critical value there and or a relative min of F prime or a relative max of F prime. And once again, that just depends. Are we going from negative to positive, or are we going from positive to negative? Okay? And so that's how we can compare the graphs or functions of F, F prime, and F double prime. Let's go to move on to our next one. Extrema. There's two types of extrema. There's absolute extrema. Those are the highest and lowest y values. How do you find it? You do it with the candidates test. And in case you guys forgot, you have your inputs here, you have your outputs here, and your candidates consist of your left endpoint coming first and your right endpoint coming last, and then critical values, all the critical values in between. And remember, critical values are the places where the derivative equals 0 or is undefined. After that, you just plug it into the function and you see which one gives you the biggest or the smallest answer. So that's how you find absolute extrema, the highest and lowest y values of a function. What about relative extrema? Well, they may not be the highest or lowest, but they are high points and low points. So we'll say that. High points or low points. So here's an example of what a relative extrema might look like. In these cases here, this one or this one, those here and here, those are relative extrema, that are, or relative maxima, I should say. Low points would look like this, or relative minima can look like that. So that's what relative extrema are. Now, how do you find them? Well, there's two ways. One way is with the first derivative test. I'm going to leave some space there because I'm going to give you some steps. And the second way is with the second derivative test. Okay, so the first derivative test works like this. You find your critical values. Once again, that's where the derivative is 0 or undefined. Then you do a number line test. And remember, positive to negative implies a max, whereas negative to positive slope means you have a relative min. I better put the words relative here. And by the way, relative are also called local. You might want to add that. And absolute are sometimes called global. It's just equivalent vocabulary, but they just don't use those words very often. Now, the second derivative test does the same thing. It also helps you find relative extrema, but it does it in a little bit of a different way. You still find your critical values. And once again, I'm going to write it up here. That's where y prime equals 0 or undefined. The derivative is either 0 or undefined. You still find your critical values, but the second step is you plug the critical values in to the second derivative. And here's our conclusion that we can draw from that. Let's scoot this thing down a little bit. There we go. Here's our conclusion that we can draw from that. If f double prime of your critical value is positive, that means your graph is concave up, which means we have a relative min. And if f double prime of your critical value is less than 0, that means that we have a concave down function, and therefore we have a relative max at that point. So there's two different ways to find relative extrema. You do need to do both. This one is probably the most useful, but every once in a while that guy will come in handy. It just depends on how much information they give you and what type of information they give you. All right, let's go ahead and move it on to the next question, or the next topic, the mean value theorem. All right, here's how it's stated. If f is continuous on a closed interval AB and differentiable on an open interval AB, then there is a value C such that the following occurs. The instantaneous rate of change at that value of C is equal to the average rate of change on the interval. And just for a graphic representation, say I have my function here. And those are the two endpoints there. The secant line tells you the average rate of change. We're looking for the tangent line that's parallel to that so that it has the same slope as the secant line. And that would be at CF of C, because at that point, the slope of the tangent line is equal to the slope of the secant line. And we call that the mean value theorem. The function has to be continuous on the closed interval, which means the endpoints have to exist. But it only needs to be differentiable on the open interval, which means we only need to make sure the slope exists between them. And that's that. That's the mean value theorem. We'll hit up a lot of FRQs on that in weeks to come, but it's related to this topic, so I thought we would talk about it here. Finally, we have the, well, I don't know, I hope this is finally. This is a long one. Yep, yay, it's the last one. Okay, so finally we have the extreme value theorem. And this rule basically just says that if a function, we'll just say if f is continuous on the closed interval AB, then there has to exist an absolute max or an absolute min. I'm sorry, and. We should say and, not or. And an absolute min. And so basically, so long as your function doesn't have any holes, gaps, or jumps, no matter what kind of line you draw, there's always going to be a minimum value and a maximum value. Okay, and that's where we come in with the candidates test after that. Now this rule doesn't actually help you find anything, it just tells you that something exists, but every once in a while they'll throw a question at you like that. But it doesn't need to be differentiable, it just needs to be continuous. All right? But sometimes in some problems they'll tell you that it's differentiable, but that's great because if it's differentiable then it has to be continuous because continuity is a requirement for differentiability, as you might recall. So we'll stop there. Hopefully that was helpful, and we'll let you guys get started on your worksheets.